Welcome. Today we're going to talk a little bit about mass spec. Mass spectrometry, unlimitedly useful, incredibly difficult sometimes, but we'll go through how it works a little bit and what we can take away from it right away, maybe even how to get a little bit more stronger in-depth information out of it. But so first, what is mass spectrometry? Mass spectrometry is essentially a technique that ionizes a molecule with various low and high energy ionizations and detects a individual molecule. Unlike most techniques we look at when we usually think of chemistry, we think of thousands and thousands of molecules, each one adding up to give a total average. Now, mass spectrometry is a little bit unique in that we look at individual molecules at one given time. So when we look at an isotope, we are truly seeing that isotope and not a mixture of isotopes. The one way we're going to think of this is kind of like World War I trench warfare, where you run over the trenches and try to get to the other side. Where every time we put a molecule in here, they're going to be putting themselves at risk of ionization. There's a machine gunner that's going to be shooting electrons out, and it's going to be hitting thousands and thousands of molecules every second. Some molecules are going to be hit with very strongly and see a lot of fragmentation. Some molecules will be barely winged and will remain largely intact. And this is going to be constantly happening. So what we're going to be able to see is we'll be measuring, in most cases, the mass over charge ratio. So assuming we have just one charge, we've lost one electron, we'll be looking at how many atoms are composed of that molecule divided by 1. Now, what are we actually looking at? So we're going to charge this ion. It's going to fly through this near vacuum situation, and it's going to reach a detector that is going to determine its mass. Now, how is it going to actually determine this mass? This mass is going to be determined by various means of separation. And from there, we can find out the molecular formula. As a quick, the main way we ionize them is electron impact. Essentially, we have an electron gun that when we have a molecule in the gas phase, it gets hit, and you're going to get various peaks. Say the molecular ion peak, which is the M plus peak, we're going to get maybe the maximum intensity peak, which is the most stable fragment, and various other fragments caused from loss of various pieces of this. Now, we're not going to look at some of the other ionization methods, but how do we then detect these guys? We detect these guys by usually either quadrupole or time of flight. That every second we have in here, in the quadrupole, every second we have essentially a gate that allows only one mass through. So of those thousands of molecules that are flying through that machine gun fire, we're only letting, say, masses with this weight through. So people that have only been winged by one bullet through, and everyone else gets left behind. And then we cycle it the next second, only letting atoms of the next mass through, and only atoms of the next mass through, and we cycle it all the way down. So every second there's maybe 50 of these ions, 20 of these ions, and 10 of these ions, and only the first one, only 50 go through. The second one, the first 50 don't go through, and we have the 20 of the next ion, and so on and so forth. And we can detect the intensity of the percentage of the million peaks in there, how many of them are of this mass, how many of these mass. Time of flight works a little bit different in that it uses the idea of momentum to determine the mass. And that mass times velocity is going to be our momentum. That each of these guys are going to be at different mass, and so they're going to have a different momentum, and they're going to allow distance to separate these guys. The heavier guys are going to move slower, the lighter guys are going to be moving faster, and so the fast guys are going to reach the essentially the detector sooner, and they can use the separation to find out how heavy these atoms are. Either way, we're going to be detecting various ions. Now, there's a couple things to note. As I said, this is dealing with individual ions, maybe thousands of them, but individual ions. So when we get a mass peak, it is literally this mass. It's not, if you get CO2, it is literally going to be 1 carbon plus 2 oxygens. So 44 mass. Typically, carbon could have an isotope, carbon-13. Carbon could have an isotope, carbon-14. Carbon-13 is what, like, I think 1% abundance. So if you have 1 million CO2 molecules, 1% of those, which would be what, 10,000 molecules, would have a mass of 45. And so you would get a small blip from 45. Now, oxygen has a 18 isotope, and that's pretty small. But there's 2 oxygens, so you would double up the chance. So there'd be a tiny blip of a mass of 46. And there'd be an even smaller blip of a mass of 48. And there, of course, might be a small blip of 47 and 49. Basically, of isotope of carbon-13 with an isotope of oxygen 18. But so you're often going to see small blips from an M+1 peak and an M+2, and they will be intensity related to the isotopic abundance. The likelihood of one molecule in a whole compound has the +1 isotope or +2 isotope. Where this is going to most be readily available, most obviously abundant, is in chlorines, where chlorine 35 and chlorine 37 have a 75 to 25% abundance. So a 25% chance of having a heavier isotope is pretty likely. Or bromine 7981, which is almost a 50-50% abundance. So those guys are going to be directly observable, and you can almost immediately tell right away if you have a chlorine or a bromine in your structure from that. There's also, of course, boron and some of the other guys with some reasonably high isotopes that you might be able to tell, but those are the 2 ones you will see most often. Also, in particularly heavy carbon compounds, ones with many carbons, you could kind of use the isotopic abundance to determine about how many carbons you have. So either way, one of the key peaks to find out is your mass peak. It's usually labeled m dot plus, meaning it has lost one electron, making it a radical. The tallest peak is the base peak, which is the most stable radical cation, which has come from when we have some fragmentation. It relates, it's the one that is most stable. And while all peaks are coming off various fragmentations and rearrangements and neutral losses, these spectra are always compound specific, but not all peaks need to be justified. Whenever you can justify a peak, that helps support a structure, but it doesn't always need to be explained. So the molecular ion will be particularly useful because it can give you a weight range. So you have some idea of what the molecular formula is. You can actually try to calculate that based on your molecular ion peak. I'm sure we're not going to have to worry about that too much. But another thing that is incredibly useful is the nitrogen rule. If you haven't ever noticed it, molecules with a nitrogen have a odd molecular mass. And this is really only true for nitrogen. There might be a few other elements, but those elements are very rare where we're going to see that, especially in organic chemistry. Every other compound can typically has either an even molar mass and can make an even number of bonds, or an odd molar mass and can make an odd number of bonds. And whenever it can do that, an odd molar mass and an odd number of bonds, it results in a even molar mass for the overall structure. Only nitrogen, with its 14 molar mass and making 3 bonds, creates this unusual dichotomy that each nitrogen compound are typically odd number. So ammonia, which is NH3, has a molar mass of 17. If I took trimethylamine, you're adding 3 carbons, 3 methyl groups, each 15, 30, 45, 45 plus 14, be 59, still odd. As long as it's a neutral nitrogen, it will have an odd mass. And for every odd number of nitrogen in a compound, you will have an odd molecular ion peak. So if you have 2 nitrogens, they cancel each other out. So you go back to having even again. So 1 nitrogen, 3 nitrogens, 5 nitrogens, all will have an odd molecular ion peak. So you can determine if there's a nitrogen in a compound. This is especially useful when paired with IR, in that, is this an NH bond or an OH bond? Well, does this have an odd molecular ion or an even molecular ion? Is this a nitrile group or C triple bond C? Well, does it have odd mass or an even mass? So you can always answer that. We're going to skip through this, but again, one thing to note is that due to fragmentation, almost all fragmentations will result in a change from even to odd or odd to even. When we lose a fragment, we're going to lose a radical, resulting in a charge. What we are actually detecting in the detector is the charge. So radicals are invisible. Neutral compounds are going to be invisible in the detector. What we're going to see is a charge. So if I have a compound A, B, C, I could lose a C to go to AB, or I could lose a C radical. Either way, so we have odd electron, mass. So, I mean, depending on how this fragments, basically, usually we're going to see a flip-flop that we're going to see various different fragmentations, usually in some sort of stable compound. For example, if we have a carbonyl group, like here, we could lose from the left side or the right side. Either way, this is going to be particularly stable in that resonance can stabilize the charge. Normally, you'd put the positive on the carbon, but by moving the lone pair down from the oxygen, you can stabilize that charge by distributing it from the oxygen to the carbon and back. So we can lose from the left or the right. We could also see a rearrangement to form loss of the R group to form this stabilized radical. I'm not going to go through the McLafferty rearrangement, but essentially we can look for losses. We can also look for losses of stable neutral compounds as being something to really look for, such as CO2, carbon monoxide, hydrocyanic acid, and water. Anytime we can stabilize a radical or stabilize a cation, we're going to see a particularly stable fragment. So this technique is also very useful for seeing monosubstituted phenyl groups, our benzenes, and our benzyl cations, which is the CH2 attached to the benzene, and that they produce resonance stabilized cations. So looking at here, what do I see? There is the mass peak is 106. The most stable loss is at 91. We have lost, what is the mass difference? We have lost 15. So what is this telling me? The most stable loss is resulting loss most likely of a methyl group. There's nothing really of note right here. There's maybe a small M+2 peak, but kind of hard to say what else. You could figure out some of the formulas, and there's some various different possible formulas we could look at. Don't worry about that so much. This one, we have a 98. We have a small little mass peak. We have the, once again, loss of 15. 69 would be what? 29, I like to say. 29, that's a 15 plus a 14. That's a loss of an ethyl group. 55 would be the loss of a propyl group. 41 would be the loss of a butyl group. And then it gets kind of confusing. So the mass peak is actually a loss of a butyl group. It could be a tert-butyl group, could be something. But 41 is also, let's see, try to figure out some of the structure. And so here's the first one. You don't really see this, it's off the screen, but we have a mass peak of 91. What that would tell me is this structure has a nitrogen in it. Structure has a nitrogen in it. And so it could be any of these structures down here. All of them adding up to 91. Okay. So one of the things that you look for, I know this isn't much. So what can we really do when we're looking at mass spec? If we're not analyzing too in depth, you want to look for the mass peak, the base peak. The mass peak can help point to what the molar mass is most likely at. You look, see if there's any abundant isotopes to help us if there's a halogen or not. And then we look to see, is this an odd mass or even mass, to whether this has a nitrogen or not. These things can give us a lot of information right off the bat that will help us with the structure. Is this the most useful thing? No, but it's a good point used used alongside synergistically with other analytical techniques is a very powerful tool to give us a good start in the right direction. So, thank you for your time.